4-1 sample spaces and probability. So we're going to talk a lot about counting principles and probability in 4-1. We need to start with some definitions and get us all on the same page with respect to what happens with probability and how to work it, and then we'll look at some examples. The first thing, we have to define probability, and that's not a period after the Y, it's the underline that goes through it, but it just appears on the other side of the Y. Probability is the chance of an event occurring, a chance of something occurring. Okay, you are familiar with the concept of probability already. Next, a probability experiment is a chance process that leads to well-defined results called outcomes. So when you conduct a probability experiment, the thing that happens at the end of the experiment is called the outcome. For example, if my probability experiment involved how many times I got a heads when I flipped a quarter, whether I got a head or I got a tail, that would be the outcome. Next is the outcome. That's what we're talking about. The result of a single trial of a probability experiment. There's one more on this slide before we move on. The last thing that we need to define is what's called sample space. And the sample space, first of all, is a set. And it's the set of all possible outcomes of a probability experiment. So in order to get to a place where we can find probability of something happening, we have to know what all the possibilities are. And the sample space represents all the total possibilities, what could happen in every situation in that particular experiment. And on the next slide, we're gonna go through and define a bunch of sample spaces for a given experiment, just so you can kind of get the feel for what it's supposed to look like. On this next screen, you can take a picture of this if you want, you can write it down if you want, but we have 5 different scenarios, and all we're doing here is we've got 5 different experiments. What I want you to do in the column to the right is write down all the possible outcomes for each of those experiments. Okay? So we'll do the first one together. Okay? If I toss a coin or I flip a coin, what are all the possible outcomes? What's one outcome I could have? Heads. What's another outcome I could have? Tails. So heads and tails, that's all I can get. Yes, we're gonna pretend that there's no possible way it could land on the edge. Okay? So my outcomes, my sample space for tossing one coin is heads and tails, that's it. That means there's 2 total possibilities. Go ahead and define the sample spaces for the last 4 experiments there and see if you can, and then we'll see if we get it right. Rolling 1 die, how many outcomes are there? 6. 1 through 6, right? How many had that? Good. Okay, answer true, false question. This is a tough one. You can either get true or false. Very good.
That one was the hardest.
Okay, now tossing 2 coins. That means the combination that you would get from 2 of the coins in succession. That is one outcome. So how many total outcomes did you have for D? 4. Okay, hopefully you had 4 total outcomes. And what are they? Heads, heads. Heads, tails.
Tails, heads.
Tails, heads. Tails, tails. Okay, that covers them all. Not necessarily in that order.
Can I tell you all the combinations for E?
No.
I just wrote
How many combinations are there going to be for E? They're actually permutations, not combinations. 36, because you can get, there's 6 possibilities on die 1, 6 possibilities on die 2. Here, if you want, you can take a picture of the screen. If you want to grab it from your book, you can as well. It's on page 184. But that is the total, that is the sample space for rolling 2 dice. Okay? There are 36 possible outcomes. Notice that 1-1 only occurs 1 time, but there's a difference between 2-1 and 1-2. Okay?
Look at this dedication right
That's very nice. Okay?
Actually,
Next, talk about a deck of cards, a standard deck of cards. And I think anymore that generations are losing touch with a standard deck of playing cards. So in case you are one of those people, I have provided what a standard deck of cards looks like. This is also on page 184, but this is something you need to know. because we will use this over and over and over again as we work through probabilities. Very common. In fact, the truth is, when you get old enough to go to a casino, or if maybe you have family members that do that already, gambling is all casino gambling is all based on probability. Okay.
I work at a casino company.
Let's just talk about a couple things here. First of all, there are what's called 4 suits. These are obviously are all hearts. These are diamonds. These are called spades, and these are called clubs. And in each set of deck of cards, standard deck of cards, there are 52 cards. There are 4 suits, and there are 13 individual numbered cards. A is for ace. Please don't say J's. These are jacks. Please don't say Q's. These are queens. And please don't say K's. These are kings. Kings, queens, jack. Sometimes aces are high. Sometimes the aces are low. It depends on the game that you are playing. Sometimes they're both. Sometimes they're high and low, or low in the same game, okay? But ultimately, what we need to know is there's 4 suits. There's the same number, 13 cards per suit. There is 4 different numbered cards, each of a different suit. And the cards themselves in the deck will always appear like this. We're not worrying about jokers for now. Okay, some card decks have jokers, some don't. Some games involve jokers, some don't. For now, we're gonna rule those out. Okay. Questions on that? How many are already familiar with this standard deck of cards and you knew all this already? Okay, good. Like I said, I see it more and more often year after year. Fewer and fewer kids knowing these. Okay, don't play card games anymore. Okay. All right. So let's talk about how to come up. Another thing that we could come up with in terms of determining sample space is using something called a tree diagram. Okay, and we're going to do a tree diagram for tossing 2 coins. Obviously, we already know the sample space for tossing 2 coins. We came up with that, and the reason I'm using that example is it's a fairly simple example, and since we already know the answer, I can show you how to use a tree diagram to confirm that. It's helpful often to keep things straight. It helps you have a system for determining the number of outcomes in a sample space. If you're just trying to come up with them off the top of your head, it's possible that you might not be sure that you've found all the possible outcomes. A tree diagram is helpful to determine that. Okay, so let's start with coin flip number 1. How many outcomes are there for 1 coin? 2. So I could either have a head and a tail. So really what this is this is the first
The first flip around
first toss or first flip. That's supposed to say that's terrible. Holy cow. First, it's hard to write with when you don't have something to rest your hand on when you're writing. That's what I'm doing here. First.
Doesn't it have a thing on it?
No. If I lean on it, it'll put it somewhere else. Okay, so the first toss, those are my 2 possibilities. Now what we have next in the second toss kind of filters over to the right. Now you can do a tree diagram moving downward too, but on this program and in the fact that I'm sort of landscape, it makes more sense for me to go to the right. Okay, so for the second toss, for this head, I can have these 2 possibilities again, heads and tails. For this tail, I have 2 more possibilities, heads and tails. So it look like that.
What the
You
frick?
keep on going down.
Okay, and so this is the first toss here. This is the second toss. And then so what you do is you follow the paths, and that gives me my outcomes. Like I said, we already knew the outcomes for this because it was a fairly simple thing, but I'm showing you how you would use a tree diagram to come up with the outcomes, because you're going to have a situation where there's going to be more than 2 possible outcomes and more than 2 trials.
Wait,
Or 2
so
experiments.
What did you do from there?
So what we do is we follow the path, okay? And so the path then tells us here, I go heads, and that really is here to that. That takes care of that row, right? Then I have another set of outcomes here. Heads, tails. So you see what I'm talking about with the system? It guarantees that I connect the possible outcomes with each trial with each possible outcome. And I could keep going down the row and matching that up. Let's say if I had tails, heads goes there, and tails, tails go there. Now, you already showed me you could do that without doing something like this. Again, my point is that you're gonna have some situations that are much more complicated than this, where a tree diagram might be really helpful to use to keep everything straight.
So would you be able to go farther than that with like heads, 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 heads?
If it said toss 3 coins, yeah. So yeah, if it said toss 3 coins, then I'd have a whole nother layer on that, and for each one of the 4 outcomes right here, they would each have 2
You
outcomes.
just have heads, tails each time after.
Yeah, it would be the same thing after that, correct? Because and the fact is it's just multiplying, right? It's exponential actually. Heads, tails, heads, tails. So every time the number of possible outcomes remains, the types of possible outcomes remains the same. The number of possible outcomes increases the further along I get. Okay. So yeah, if I wanted to do toss a coin 3 times, I'd have another layer here. If I wanted to go 4, I'd have another one there. And we're gonna look at a tree diagram with 4 layers in a minute. Okay. All right, let's talk more about some definitions so we can figure out some probabilities. Okay, an event is a set of outcomes from a sample space. Now that could include some of them. It could include one particular trial within an experiment. It could mean something very specific, like the probability of one particular thing in that sample space occurring. Got a couple more definitions too. We have a simple event when there's only one possible outcome. So all of this information is leading us to a place where we can actually find probabilities of things happening or not happening. So we just got to get
the sample event would be the white one toss.
No, there's one possible outcome. One outcome. Okay. We have a compound event with 2 or more outcomes. Okay. And then we have definition. This is on page 186. So here's how we actually find probability. Okay. So the number of outcomes in the event that we're looking for divided by the total number of outcomes. Okay, so it's like the desired outcome divided by total number of outcomes. So for example, if I wanted to know out of flipping a coin twice, the probability of getting heads, heads, 25%, or 1 out of 4, right? There's only one way to get heads, heads. There's 4 total possible outcomes for flipping a coin twice. So that's how probability works. The number of outcomes for that event in particular divided by the total number possible outcomes. And this notation down here just means number of outcomes in event E divided by number of outcomes in the sample space. Okay, that's the probability of an event occurring. How many of you worked with probability before?
Is that N?
Yeah, number of. Have you guys ever done probability in any classes before, really?
Yeah.
Maybe middle school. It's probably been a while. Yeah.
Isn't it just percentages though?
It can be percentage or fractions. We're gonna get into that a little bit more. Okay. We need to get on the same page with some probability rules to make sure we're all speaking the same language. So that's the next thing, probability rules. What is the largest possible probability of something happening? 100%, or if we didn't want to express it as percent.
1 out of 1.
1. So either if something is definitely going to happen, it has 100% probability of happening, or it equals 1. And now Nick joked about it earlier. There's probably a little bit of truth to it, but I think he said, what did he say? The probability of Jake staying quiet is 0, right? Which means what? What does that actually mean?
It's not gonna happen.
It's not gonna happen, 100% not gonna happen. That's why I said it's probably close to 0, not exactly 0. It's likely. Yeah, well, he gets sleepy. He always gets sleepy. But so what we have to understand is that the probability of any event is bounded on the lower end by 0. It could equal 0. It can be as high as 1, but it can never go over 1. So the sum total of all probabilities has to always be in there. Okay? It can't exceed 1, and it can't be less than 0. And that's all that this means. The probability of an event, any event, has to be in between 0 and 1 inclusive. So we just talked about. If an event cannot occur, there's no chance that it can happen, then the probability of that event is 0. If it absolutely 100% cannot happen, then the probability of that event is 0. If you're rolling dice, and you said, what's the probability of rolling an 8 with a regular die? There's no chance for that to happen. A regular die is numbered 1 to 6. You can't roll an 8, so that would have a probability of 0. Conversely, if it is certain to occur, it's absolutely 100% going to happen, then the probability of that event occurring is 1 or 100%. Okay? I'm not going to get hung up on whether or not you use fractions or decimals or percents unless it's strictly written in the problem in terms of what it tells you to put it at, put it in fractions or decimals or percents. Otherwise, I'm going to leave that up to you. And lastly, as I mentioned earlier, the sum of all the probabilities in one sample space has to equal 1. If I have all the probabilities within that one particular sample space and I added them all up, the sum of all those probabilities must equal 1 because it covers everything. So if I said, for example, with a regular die, what's the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6? That would be 1. Because when I roll a die, it has to be one of those because I use the word or. If it was one of those, and we'll get into that more a little bit later. But the sum of all probabilities in a sample space must equal 1. The complement of an event. The set of all outcomes in the sample space that are not in E. So the complement is everything but event E. That's the complement. And there's a little formula to find the probability of the complement of an event. Okay? To find the probability of the complement of an event, you subtract the probability of the event from 1. Because the probability of the event plus the probability of the complement added together will equal 1. So here's the example I want you to take a picture of. Okay? Take a picture of that and let's talk about, and actually why don't you go ahead and try to answer that. What they're saying here, 16% of American children say they use flattery to get their parents to buy them things. I think that number has to be low. But if they randomly select a child, what's the probability that they're not going to use that tactic? Okay? So really it's the opposite of the 16%. So that's where the 1 minus the event. So the event is using flattery. The complement of the event is not using flattery. So 1 minus that. So yes, it's how much? What's the percentage?
84%.
80%. Okay? How many had that? Good.
Because it's gonna get harder, like.
Since this problem is written in percent, you could think of this 1 as 100%. So 100% minus 16% is 84%. Okay? And the key word here is not. They do not use flattery. If 16% use it, the percentage that don't use it is 1 minus 16, or 100% minus 16%. All right, let's look at some examples, and I want you to try to figure out the probabilities for them, okay? We're back to our deck of cards. So if we have a card is drawn from an ordinary deck. We're drawing one card out of the deck, okay? What I want you to try to do is find the probability of getting a king. That's one experiment. What's the probability of getting a king out of a deck? Write that down, write it as a fraction, and simplify that fraction. Then do the same thing for B. What's the probability of getting a red king? And C, the probability of getting a 7 or a heart. Let's talk about this one, okay? Probability of getting a king. How many kings are in a deck? 4. So this starts off as 4 out of 52. It reduces to
2 divided by 26 or 1 over 13.
1 over 13. The probability of getting a king is 1 out of 13. How many had that? Okay, good. A red king. How many red kings are in a deck? 2. There's a king of diamonds and a king of hearts.
I didn't reduce them.
So this should be 1 over 26. Here's the thing I want to make sure that you do, and hear loud and clear. If you do not reduce your fractions on a quiz or test, I will take points off. It does not need to say that. That just needs to be understood.
We'll say minus 1 over
Okay. Now, for this one, the key word here is or. There's 4 sevens, right? There's 4 sevens in a deck. How many hearts are in a deck?
13.
13. So is it 17 out of 52?
16 because
Why?
one of the sevens is inclusive.
Right, so one of the sevens is here, or sorry, there's a 7 of hearts in here. There's also a 7 of hearts in here. We don't count it twice. So what we actually have to have, there are 16 possible ways to get a 7 or a heart, which is 4 out of 13. How many had that? How many caught the fact that there was a 7 of hearts and that counted in both places? Okay, good. The last thing, and I'm going to kind of help you through this last thing a little quicker than you having to do it all by yourself. But when you get to your homework, you're going to have to do something like this. So this problem says a family has 4 children. And find each probability. So the probability that a family has 3 boys, the probability that the oldest child is a girl, meaning that child that came first, or that the probability that they are all girls. Now, in order to figure this out, you need to know the sample space of a family with 4 children. And there's not a real easy way to do this. And so I'm going to provide you with a tree diagram for this situation. Obviously this is very similar to the heads and tails, right? Because we're going to, for the purposes of this experiment, we're going to all agree that the only possible outcomes are either a boy or a girl. We're not getting into some social discussion about anything else. Okay? We're having either a boy or a girl. Which means it would essentially have taken that tree diagram that we did for heads and tails to 4 tosses instead of 2. Okay, and it's the same kind of thing. So here's what it looks like. I want you to take a picture of this. Okay, and let me squeeze it in there so it all fits.
Is it 16?
We're not doing a tree diagram
No.
like that for homework?
It's not.
Hold on.
It's fine.
Not me.
Whoa.
I want to get it all to fit on there. Okay, there you go. There is what the tree diagram for boys and girls is all the way out for 4 children. Okay, so this column here is the first child, the second child, the third child, and the 4th child. And then I went ahead and abbreviated all the outcomes. So yes, there are 16 possible outcomes. However, now what I want you to do from this is find the probability of 3 boys. Find the probability that the oldest is a girl. Find the probability that they are all girls. Go ahead and find those probabilities from that set of outcomes. Go. I'm actually gonna start with C because it's super easy. How many possibilities in this set of outcomes, this sample space, has all girls? 1. This is the only one. So the probability of a family with 4 girls equals 1 out of 16. Okay? Now, let's go to B next. The oldest is a girl. That means the firstborn child is a girl. Half of them. There's 1, 2, 3, 4, 5, 6, 7, 8 where the girl comes first. That is 8 out of 16, which is 1/2. Okay? Now for the ones that have 3 boys. Now it doesn't say what order they have to be in. So what you have to do is go through this list and find the number that has 3 boys in it. Okay? So I've got, let's ask this.
1.
Is this count?
No.
Yeah,
It has
3 boys.
4 boys.
It has 4 boys. Is that 3 boys?
No, that's 4.
If it said at least 3 boys, that would be different, but it doesn't say that. So we don't count that one. I count this one.
2, 3, 4. The end.
Did it?
No.
Yep, that's it. There's only 4 of them. So there's 4 out of 16, which is 1/4. Okay?
Do we not put these in percents?
You can if you want. I'm telling you, you don't have to. I don't care. As long as it's equivalent.
We're gonna miss